Understanding the frequency response of transistor amplifiers requires analyzing both low-frequency and high-frequency behavior. Internal capacitive effects within transistors determine the limitations at high frequencies. This video will cover the high-frequency model of the MOSFET and BJT. The MOSFET's physical structure gives rise to internal capacitances. While we initially assumed instantaneous charge acquisition, a finite time is required to charge and discharge these capacitances. This time-dependent behavior is critical for accurate high-frequency performance prediction. In the saturation region, the N-channel MOSFET exhibits a tapered channel pinched off at the drain end. 4 key internal capacitances are present: CGs, CGD, CSB, and CDB. These are crucial for high-frequency circuit design. The 4 internal MOSFET capacitances are CGs, the gate-to-source capacitance, and CGD, the gate-to-drain capacitance, both arising from the gate capacitance effect. Additionally, we have CSB and CDB, the source-to-body and drain-to-body depletion capacitances, respectively. The gate capacitance effect is modeled by the polysilicon gate forming a parallel plate capacitor with the channel, using the oxide layer as the dielectric. The gate or oxide capacitance per unit area is denoted as COX. Overlap capacitances are small capacitances resulting from the gate extending over the source and drain regions. These overlaps, each with length love, contribute to the total device capacitance. The overlap capacitance is calculated using the formula shown. The total gate-to-source capacitance, CGs, is the sum of 2 components: the channel component, which is 2/3 of the total gate capacitance, and the overlap component, COV. The total CGs is the sum of these two. Due to channel pinch-off in saturation, the gate-to-drain capacitance, CGD, consists entirely of the overlap component, COV. Although small, CGD is critically important because it contributes significantly to high-frequency limitations via the Miller effect. The source and drain diffusions form reverse-biased PN junctions with the substrate, or body. These junctions result in depletion layer capacitances, CSB and CDB, which are voltage-dependent. Their formulas are derived from fundamental semiconductor physics. The source body capacitance, CSB, varies with the applied reverse bias voltage. The formula shows its dependence on the zero bias capacitance, CSB0, the reverse bias voltage, VSB, and the junction built-in voltage, V0. The drain body capacitance, CDB, follows the same voltage-dependent relationship. The formula uses CDB0, the zero bias capacitance, and VDB, the magnitude of the reverse bias voltage. These formulas typically assume a grading coefficient of 1/2. These are typical MOSFET capacitance values for a 0.5 micrometer CMOS process operating under specific bias conditions. Note the relatively large CGs compared to the small CGD and the body capacitances. This figure shows the complete small signal model of the MOSFET, including all 4 capacitances: CGs, CGD, CSB, and CDB. While too complex for easy manual analysis, this comprehensive model is essential for accurate high-frequency computer simulations using tools like SPICE. When the source is connected to the body, the CSB and VB's terms are eliminated. The resulting simplified model retains CGD and CDB, streamlining the circuit for further analysis. The high-frequency equivalent circuit can be further simplified. Often, CDB is neglected to ease manual analysis, leading to a common simplified model. And finally, the high-frequency T model. CGD is critical and must be kept in the model because it creates the Miller effect, significantly affecting high-frequency response. Conversely, CDB is often negligible and can usually be removed to simplify manual calculations without major loss of accuracy. Model simplification progresses from the full model to the source body connected model, where CSB is eliminated. Further simplification involves neglecting CDB, leading finally to the high-frequency T model, which is useful for manual analysis. The unity gain frequency, FT, also known as transition frequency, is a key metric. It is the frequency where the short-circuit current gain of the common source configuration drops to unity. It signifies the device's high-frequency capability. To determine the short-circuit current gain, we use the hybrid pi model. An input current signal, 2, is applied to the gate, and the output terminals are short-circuited to measure the output current, I/O, at the drain. The output current is expressed by the formula shown. Since CGD is small, The second term can often be neglected at the frequencies of interest. This approximation simplifies the analysis significantly. The input voltage, VGs, can be expressed in terms of the input current, 2I. This relationship confirms that the input impedance is purely capacitive, where the total capacitance is the series combination of CGs and CGD. Combining the output current and input voltage expressions leads to the short circuit current gain formula. For physical frequencies where S equals J omega, the magnitude of the current gain simplifies to the expression shown. Setting the current gain magnitude to unity allows us to define the unity gain frequency, omega t. Converting to hertz gives us the final formula for Fort, which is directly proportional to transconductance and inversely proportional to total gate capacitance. A higher transconductance, GM, leads to a higher mid-band gain and better high-frequency performance. Conversely, internal capacitances limit bandwidth, meaning smaller capacitances enable higher frequency operation. Thus, FT is an overall figure of merit. Technology scaling has drastically improved featuring values. Older 5-micrometer CMOS devices had featuring around 100 MHz. Modern advanced nodes now achieve featuring values exceeding 10 GHz, enabling high-speed applications. Table 10.1 provides a comprehensive summary of the MOSFET high-frequency model. It details the circuit topology and includes all key parameter equations, offering a centralized reference for design and analysis. This slide is for reference and summarizes the high-frequency small-signal equivalent circuit of the MOSFET. This slide is for reference and shows the relationships between key parameters of the MOSFET high-frequency model. Design trade-offs exist for achieving a high featuring. Increasing the with-L ratio or the overdrive voltage increases GM, but also increases capacitances and power. Using advanced technology is the best way to inherently reduce capacitance. Model parameters depend on several factors: process parameters like mobility and oxide capacitance, design parameters like W, L, and bias current, and operating conditions such as body voltages and temperature. Accurate high-frequency models are vital for modern circuit design. Without including internal capacitances, gain predictions would be constant, which is incorrect. These models predict bandwidth and speed before device fabrication. High-frequency analysis is applied in various areas. It's crucial for designing RF amplifiers for wireless communication, predicting propagation delay in digital circuits, and ensuring stability in high-frequency oscillator design. The Miller effect significantly magnifies CGD's influence. Since CGD connects the input and output nodes, its effective input capacitance is multiplied by 1 plus the voltage gain, making it critical despite its small physical size. Technology scaling impacts featuring through reduced dimensions and thinner oxide layers. Generally, each new technology generation aims to double the unity gain frequency, constantly pushing performance limits. Measuring high-frequency parameters requires specialized techniques. S-parameter measurements using vector network analyzers are commonly used, and de-embedding techniques are necessary to remove measurement system parasitics. Temperature affects performance by degrading carrier mobility, which decreases transconductance and featuring. It also influences the threshold voltage and operating point, while junction capacitances show a weak temperature dependence. Long-channel devices are dominated by channel capacitance, exhibit classical behavior, but have lower featuring. Short-channel devices have significant overlap capacitance, show velocity saturation effects, and achieve higher Fort, but with lower output resistance. Practical design requires choosing the appropriate with-L ratio, optimizing the bias point for maximum Fort, minimizing parasitic capacitances through careful layout, and ensuring the design is robust against process variations. Advanced topics in high-frequency analysis include non-quasi-static effects, distributed gate resistance, substrate network modeling, and noise analysis. These are essential for millimeter wave applications. The process of simulation and verification involves 4 steps: extracting model parameters, building the SPICE model, running AC analysis to simulate frequency response, and finally, verifying the results against physical measurements. Internal capacitances significantly impact circuit topologies. In a common source configuration, the Miller effect from CGD limits bandwidth. Conversely, the common gate configuration avoids the Miller effect, offering potentially higher bandwidth and lower input capacitance. Several techniques extend bandwidth. The cascode configuration reduces Miller multiplication, significantly extending bandwidth. Inductive peaking uses inductors to resonate with capacitance, and negative feedback trades gained for wider bandwidth. Key takeaways include that internal capacitances are fundamental and unavoidable. The unity gain frequency, FT, is the key metric characterizing high-frequency capability. Accurate models, including capacitances, enable precise prediction of frequency response. Design guidelines summarize maximizing the transconductance to capacitance ratio to improve featuring. Minimize the impact of CGD by reducing the Miller effect. Choose optimal bias conditions to balance speed and power, and leverage advanced technology when speed is critical. Understanding MOSFET internal capacitances and their impact is essential for modern circuit design. The high-frequency model enables accurate behavior prediction, and featuring serves as a fundamental figure of merit for performance as technology continues to scale.